Hey there, folks. It's time to take a look at homework for 4.3. These are homework problems. For the most part, I think we're intended to use combinations and the calculations for counting combinations. So let's get going. Problem 5A says 11 horses run in a race. Jake wants to bet $1 on a slate of horses to win, place, and show. Now that's a little confusing in that when I first read that, it wasn't clear to me whether you had to pick the winner, pick the placer, and pick the shower. Just because we're working in the section with combinations, the section of the book on combinations, I'm going to assume it just means you're picking 3 horses and they finish in the top 1, 2, and 3 places. You know, the top 3 places. So that's the way I'm going to work the problem. I think we talked about this in class, actually, that there's different ways to do this, right? You could pick the winner, pick the place, pick the third place. But I'm assuming here that you're just picking the top 3. So, okay. And how many ways might he pick the horses for this bet? Well, we've got 11 horses here, and we want to choose 3 of them because it doesn't really matter. You're choosing 3 in a collection, no order. So that would be 11 choose 3. So the arithmetic on this is 11 factorial over 3 factorial, and then 11 minus 3 factorial. I'll go ahead and write it out. So this 11 factorial over 3 factorial and 8 factorial. To do the calculation, you can either use a button on your calculator or get rid of the 8 factorial. And then 3 times 2 times 1 here. 3 goes into that 3 times, into this 5 times. So this is 15 times 11 is 165. You know that little trick about multiplying by 11, don't you? You take the 1, you take the 5, and you add the 2 right there to get the middle one. Okay. Part B says Jake decides to stay for 4 races and bet on a slate of horses to win, place, and show in each race. First 2 races have 11 horses each, so that would be a repeat of the first problem. The third has 10, and the fourth has 8. How many possible options does he have for making his bets? Well, we've got a first race, a second race, a third race, a fourth race. Right? So once we have the numbers for each race, we can just multiply to get the total number of options. So let's take a look at the first and second race. We've already got the number on that. Third race, there are 10 horses, and he's choosing 3 in no particular order. 10 factorial, 3 factorial. I'm going to start doing this in my head. 10 minus 3 is 7 factorial. Okay, I've shown you where that comes from. You do a subtraction problem, and it's that factorial. So this is 10 times 9 times 8 times 7 factorial, which will cancel with that 7 factorial, and then 3 times 2 times 1, and then 3 and 4. So this is 12 times 10, which is 120. In the fourth race, there are 8 horses to choose 3 from. So this is 8 factorial over 3 factorial times 5 factorial. That's 8 minus 3, right? And I'm also going to start leaving out this little factorial cancellation. So this is 8 times 7 times 6 over 3 times 2 times 1. That's 6, and so this is 56. So total options now would be, you've got the 165 for the first race, and the 165 for the second race. Got the 120 for the third race, and the 56 for the fourth race, which turns out to be 182,952,000. Okay. All right. Okay, so that's problem 5. Problem 8 says, okay, 5 cards are dealt from a standard deck of 52. How many outcomes are possible if the order of the 5 cards is irrelevant? That would certainly be the case if you just got a hand of cards, right? You can move them any order you want to. So we've got 52 cards, and we need to choose 5 of them. This is 52 factorial over 5 factorial, and then 47. That's 52 minus 5. So this is 52 times 51 times 50 times 49 times 48, and then 5 times 4 times 3 times 2 times 1. And the 47 factorials are canceled out. So let's see, 5 times 2 is 10. Let's see though, 5 goes into 5 10 times, and then 2 goes into that 5 times. And let's see, 4 goes into 52 13 times, 3 goes into 51 17 times. So whatever 13 times 17 times 5 times 49 times 48 is, let's see, on my paper I get that to be 2,598,960. Okay, different 5-card hands you could get from a standard deck. Part B says how many of these outcomes consist of 3 aces and 2 kings. All right, now we now have categories of cards. I've got my aces, I've got my kings. So once I calculate the number of ways of getting the aces and the number of ways of getting the kings, then multiply and that'll tell you how many ways to get that hand. Okay. So, all right, so let's just do them separately at first. Aces, I've got 4 aces in the deck and I want to choose 3 of them. That's going to be 4, right? I can leave out this one, leave out that one, leave out that one, leave out that one. That's the 4 ways to do it. But if you do the arithmetic, you'll see that 3 factorial, 1 factorial. So that's just, you know, when you cancel out the 3 factorials, you're just left with the 4. And then getting the kings, you've got 4 kings in the deck and we want to choose 2 of them. So 4 factorial over 2 factorial, 2 factorial. 4 times 3 over 2 times 1 is 6. So total would be 4 times 6, 24 different outcomes. Okay. These are kind of cool counting. I like these kind of problems actually. I think they're kind of neat. All right, let's do problem 9 now. To create a secret code, Gaston removes 15 of the 26 letter keys on his keyboard and randomly replaces the keys into the 15 vacant positions. Then when he types a message using the new key positions, some keys produce a different letter from what they indicate, making the message difficult to decipher. The hard part for me would be not typing the way I'm used to typing. Even if you move the A key, my finger seems to know where the A key is. I'd have to make myself, you know, not go there. Yeah. So, okay, so how many ways can he remove and scramble the 15 keys? And these are 2 separate processes, right? First you remove, then you put them back on. So if we do this separately, let's see, removing, we've got 26 keys there, and I want to choose 15 of them that I will remove. So this is 26 factorial over 15 factorial over 11 factorial, which is kind of messy if you do it out. I'm just going to go ahead and produce the number. This is 7,726,160 different ways of doing that. And then there's the replace. This is actually an easier calculation, right? You got 15 choices for the first empty key, 14 for the next, 13 for the next, all the way down. So this is 15 factorial. So total here then is the 26 choose 15 number we just calculated times 15 factorial, which is a relatively small number. Let's see, million, billion, trillion, zillion, quintillion, I think is the way. So 10 quintillion, 103 zillion, 301 trillion, 395 billion, 66,880,000 different ways to do that. That's a great big number. Okay, and it really does illustrate one of the things we talked about in the last homework set, in that you can do very simple things. And then when you ask the question of, well, how many different ways can you do that, you end up with just bukus of different ways of doing that. And especially when you get these factorials involved, it gets big in a hurry. So that was kind of a cool problem to illustrate that. All right, on to problem 10. For his new aquarium, Trey wishes to select 4 to 7 fish, each of a different type. Now, this is important. It means that they're distinguishable items, right? We've talked about in class the difference between, working with distinguishable items. Oh, I can tell that one from this one. And then having things like letter ends floating around that you can't tell the difference about, right? But you're going to select 4 to 7 fish from 14 different types that are compatible. That means they can all stay in the same water and not eat each other. How many outcomes are possible for his selection? Now, there's a difference here, right, between 4 to 7. I think we have to handle this as separate situations. He goes in and picks 4, or chooses 4. It doesn't matter what order they're chosen in. They're all going in the tank. Or he does 5, or he does 6, or he does 7, right? So these are all separate ways. They're not like a series of selections. He's not doing this and this and this and this. He's doing this or this or this or this. And when you're doing these things, and is a tip-off that we're multiplying, or is a tip-off that we're adding. Okay. Okay, so we calculate all these different outcomes and then add them together. So if we're choosing 4, this is 14 factorial, 4 factorial, and 10 factorial. So this is 14 times 13 times 12 times 11 over 4 times 3 times 2 times 1. 4 times 3 is the 12. The 2 here is probably gives me a 7. And I think when you do all this out, you get 1,001. Okay. And if you remember your divisibility test, you realize, oh yeah, that's divisible by 7 and it's divisible by 11, right? If you remember how that all works. Okay, so. And then 14, if we choose 5, this is 14 factorial over 5 factorial and now 9 factorial. So 14 times 13 times 12 times 11 times 10 times 5 times 4 times 3 times 2 times 1. The 9 factorials are canceled out there. 5 times 2 is 10. We'll get rid of that. 4 times 3 is 12. We'll get rid of that. And so this is the same number, except now I've got 14 in time. I have 14 instead of 7. It's twice the number, so this is twice the number. 2002. If he decides to go with 6 fish, this would be 14 factorial, 6, and then 8. So 14 times 13 times 12 times 11 times 10 times 9. 6 times 5 times 4 times 3 times 2 times 1. 6 times 2 is 12. We can get rid of those. Let's see, 5 goes into that twice. 4 goes, I got a couple 2's here, so 7, and get rid of that one. 3 goes into 9 3 times. So I think when you do that that problem, you end up with 3003. Kind of a curious pattern going there. It doesn't last. When we go to 14, choose 7. (14 times 13 times 12 times 11 times 10 times 9 times 8). 7 times 6 times 5 times 4 times 3 times 2 times 1. So let's see, 7 into that twice, 6 into that twice, 5 into that twice, 4 into that twice, 3 into 9 3 times, and then get rid of one of your 2's. So I think that works out to be 3,432 by my calculator. Okay, so then the total outcomes, we just add these things up. And I believe that outcome, that number is 9,438 if my calculator and my hand here are on track. Okay. And then one last problem. Kind of gives a highlight between that. Was kind of an or problem. You had different things that could happen, this or this or this or this. This is an and. You got a Tokyo High School and a Baltimore High School. They have an exchange program in which 8 seniors from each school spend 2 weeks at the other school. If the Tokyo High School has 120 seniors to choose from, the Baltimore High School has 132 seniors to choose from, how many outcomes are possible for the exchange? You have to choose both, right? You get 8 here, you get 8 there, and then you swap them. The 8 you choose are in no particular order, so it will be combinations. But then when we get this number and we get this number, the way to complete the task is you do this and you do this, multiply, and get the answer. So, and I'm going to skip, these are some big numbers, so I'm going to skip some of the calculations on this one and just go straight to the numbers. To get the students, the seniors in Tokyo, you've got 120 and you need to choose 8 of them. If you get down to doing the calculation on this, it would be 120 factorial over 8 factorial and then 112 factorial. But these are big numbers. The way to do this probably is break it down or just go straight to your calculator. This is 840 billion 261,910,995. And then for Baltimore, it's 132, choose 8, which I'm just going straight to the number. It's 1,841,000,000,000, billions and billions, 416,434,000. So the total number of ways to do this, you multiply. You're taking the 120 choose 8 times the 132 choose 8, and this is ginormous. I think I attempted to do this in class, but I'm just going to write it out. Four, 3, 8, 1, 5, 4, 7, 2, 7, 2, 0, 9, 1, 7, 7, 0, 4, 3, 8, 2, 9, 1, and then 830,000. That is a big number. But again, it does highlight the thing I was saying earlier. This is a very simple thing to do, right? Sounds easy, and you'd think it wouldn't be that. If you talk about, well, how many ways can you do that, you wouldn't think that would be a huge number. It is a huge number. Okay. All right. That's it for the homework then, from 4.2 and 4.3. You can hand that homework in on Tuesday, and I'll get it graded for you. Hopefully on Tuesday I'll have your test graded. The homework that you handed in, I'll have that graded, and then we'll start working the problems from the last lecture, okay, on indistinguishable things using the multinomial coefficient, and then also counting multisets using the stars and bars and the multiset counting, okay, the multi-choose notation that we use. All right, see you later.